In section 7.2, we're talking about sample proportions. So the three learning targets are calculate the mean and standard deviation of a sampling distribution of a sample proportion and interpret the standard deviation. Determine if the sampling distribution of p hat is approximately normal, and then if it's appropriate, use a normal distribution to calculate probabilities involving the sample. So remember, a sample distribution of the sample proportion describes the possible values taken by the sample proportion in all possible samples of the same size from the same population. So here's a little example of taking a sample of size 20, taking 50 samples of size 20 from a bag of pennies, and calculating the proportion of pennies that were made in the 2000s. So like this p hat right here, it's approximately 0.35, represents one sample of 20 pennies that resulted in 35% of them being from the 2000s. So here we have a distribution of samples where each p hat is an individual sample. The idea behind this section is to understand how to take some samples and estimate what the sampling distribution would have as far as the shape, center, and variability of the standard deviation. So here we have 6 graphs. We're really going to break this up in columns. So here on the left-hand side, we have a small proportion, 0.10. So this is saying if the proportion of, let's say we're talking about the pennies, the proportion of the pennies that are from the 2000s are just 10% of all pennies that are in there. But then notice we have a different sample size, 25 versus 100. So the difference between these two graphs is you can see if I draw a smooth curve up top on here, this is fairly skewed right, whereas the bottom graph, approximately normal. Well, we can say the same idea happens when we go to the far right, when we have a proportion closer to 1, so we have 0.9, sample size remain the same, but the curve up top is skewed left, versus the bottom, it's approximately normal. So notice we have a skewed right distribution and a skewed left whenever the sample sizes were fairly small, 25, but when the sample sizes were large, 100, they became approximately normal. So the reason why this first graph on the left with the proportion of 10 is skewed right is because if the true proportion of pennies in the 2000s in our bag that we're pulling from is only 10%, then we're expecting a lot of values around the 10% value. But that means there's going to be a few that are over here in the greater. Then the converse, I guess you could say, of that is if we have a high proportion of them from the 2000s, we're expecting samples that showcase a lot of them. But there's going to be a few that we just by chance do not get many from the 2000s. So that's why we have the left and the right skewed distributions based on the high and low proportion of what we're looking for. But again, as our sample size is large, it actually becomes approximately normal. Then here in the middle, we actually have both being approximately normally shaped graphs. But notice that our proportion is in the middle, 0.5. So the sample size doesn't actually change the overall shape that much, but it does dramatically decrease the variability. So here in general, top row, bottom row, the larger the sample size, the less variability there will be, and the larger the sample size, the more normal the graph will approximately look. This is just recapping all of what I said about those 6 graphs. So here we have a generalization on how to determine the mean and the standard deviation and the shape of a sampling distribution of a sample proportion. So if we're choosing a random sample, the mean of the sampling distribution, mu sub p hat here, is going to equal whatever my parameter value is. The standard deviation can be calculated using this formula, which is given on your formula chart, if as long as your 10% condition is satisfied. This is the same condition what we were dealing with before Christmas with the binomial distribution, that our sample is less than or equal to 10% of our population. So we check this 10% condition first, and if it is satisfied, then we can calculate the standard deviation. Then to determine the shape of the distribution will be approximately normal if we have our large counts condition, that n times p and n times 1 minus p are both greater than or equal to 10. So again, we check that both of those values are greater than or equal to 10, and if they are, then it's approximately normal. Remember, the idea is we're eventually going to be asked to calculate probabilities. So if we can show that it's a normal distribution, then we can use all those rules with normal curves in order to find the probability. So let's go through an example. So suppose that 84% of students at a large high school regularly use a backpack to carry their books from class to class. Imagine taking a simple random sample of 100 students and calculating p hat to be the proportion of students in the sample who regularly use a backpack. So part A, identify the mean of the sampling distribution. Well, the mean of the sampling distribution is going to be the actual parameter value, which is 84%, so 0.84. Part B says calculate and interpret the standard deviation. Well, we need to make sure that our 10% condition is satisfied. So if we assume that our sample, we can assume that our sample of 100 students is less than 10% of all students in a large high school. Again, large high schools usually deal with the public schools, so thousands and thousands of kids. So because that's satisfied, we can use that formula, the square root of p times 1 minus p over n, to calculate the standard deviation. Then it said to interpret. A lot of students forget the second part, and interpret. So in a simple random sample of size 100, the sample proportion of students who regularly use a backpack will typically vary by about 0.0367 from the true proportion of p equals 0.84. The standard deviation here is interpreted the same way as it always has been. It's the typical distance of how something varies from the mean. Then the last part, C, describe the shape of the sampling distribution. That's where you do your large counts condition. Check that the sample size times p and the sample size times 1 minus p are both greater than or equal to 10. If they are, like they are in this case, then we can say the sampling distribution is approximately normal. So that's an example of checking all of those conditions. But what we're actually wanting to do is find probabilities. So here, a polling organization asks a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. Find the probability that a random sample of 1,500 students will give a result within 2 percentage points of the true value. So our center is going to be 0.35, because it's going to be the same as what is given here. We can assume that 1,500 is less than 10% of all first-year college students, because that's all over whatever country or the world or whatnot, because it does not give us much of a parameter there. So then we can calculate standard deviation. So we get 0.0123. And then because n times p and n times 1 minus p are both greater than or equal to 10, then we know it's approximately normal. So based on these three items over here, we can create a visual. I think a lot of students benefit from drawing the graph because it gives them a better idea of what they're actually trying to calculate. So here we can standardize the scores if we want, or use our calculator. We have multiple options. So after graphing this, we have our center of 0.35 going out 1 or 2 percentage points. That'd be 0.37 and 0.33. It's in between some standard deviation values. So we need to figure out what these values are as a z-value, and we can use the z-table to find the proportions or the probability for each value and then subtract them, or we can use our calculator. So let's go through both. So finding the z-value that represents the 0.33 and the z-value for 0.37, remember that's the actual number of standard deviations away from the mean. They will give us the same number of standard deviations because they're the same distance from the mean, being 2 percentage points from the mean. So looking at our table at negative 1.63 and positive 1.63, we would take them and we would subtract, because the positive 1.63, when you look that up on the table, it's going to give you the entire area from under that curve. But we don't want this that's below the 0.33. So the value we get from below 0.33, we will subtract that so that we're only left with the area we're looking for. So that area will become, or you will find, is 0.8968. You could also find those z-scores, and instead of using the table, you could use the normal CDF function and use those standardized values. This should say negative, not positive, negative 1.63 to positive 1.63 with a mean of 0 and 1 because you've standardized them. And it will give you a decimal fairly similar to one you got using the table. Now remember, you cannot use norm CDF as justification. You cannot use calculator language to get credit. All the conditions that we checked plus this graph is plenty of valid justification as to why you get whatever answer you do get. You could also strictly use your calculator and not actually find the z-values. So you would do this by doing the normal CDF function, doing the 0.33 to 0.37, your mean is 0.35, and our standard deviation is 0.0123. Notice that this decimal is quite different. Not really that different, but still quite different from the ones we got. That's the difference between by hand and using the table versus the calculator. Make sure whichever method you choose, you're using that method throughout the entire problem and not switching up in between.